On the modern field of operation, a single piece of gear stands as the primary line of defense: the advanced combat helmet. It must withstand high-velocity impacts and extreme conditions. But how is this level of protection actually engineered?
It begins here, not with heavy metal, but with a high-tech fiber called Ultra-High Molecular Weight Polyethylene. Pound for pound, this synthetic thread is 15 times stronger than steel and light enough to float on water.
At this secure manufacturing facility, raw fiber enters a massive automated loom to undergo transformation. The machine weaves the strands into a cross-ply architecture. One layer is horizontal, the next is vertical. This cross-hatching is the secret physics. It catches high-velocity projectiles like a net catching a ball.
Precision automated cutters slice the fabric into specific geometric shapes. Every millimeter is calculated to reduce waste.
We aren't making clothing here. We are cutting the fundamental layers of a personal shield.
Operator Mike begins the layup process. This is where skilled human touch meets high-tech material science.
Each helmet shell requires exactly 28 to 30 independent layers of this composite fabric to function correctly.
If the stack is too thin, the protection fails. Too thick, and the equipment becomes too heavy for the wearer.
The stack is placed into a preformed fixture to give it a rough geometric shape before the main event.
Wrinkles are the enemy. A single crease creates a weak point in the structural integrity of the composite.
Right now, it is pliable. You could crush it with your hand. But the laws of physics are about to change that.
The mold is coated with a release agent to prevent the composite material from fusing directly to the steel.
Enter the molding bay. These hydraulic presses can deliver over 3,000 tons of downward force.
The soft preform is loaded. The mold temperature is set to a scorching 250 degrees Fahrenheit.
Slowly, the jaws of the press descend. There is no turning back once the cycle begins. Under this heat and pressure, the resin inside the fibers melts and bonds the layers together permanently.
It's called thermoset consolidation. We are fossilizing the fabric into a single, rigid monocoque shell.
The cycle is complete. The press releases its massive grip on the mold.
What went in as a soft blanket comes out as a rigid shell, hot to the touch. For the next 15 minutes, the material cooks. The chemistry of the fibers is being fundamentally altered.
Listen to that sound. It is no longer fabric. It is a solid piece of armor.
But look at the edges. They are jagged and sharp. The excess material must be removed immediately. A robotic arm grabs the shell. It prepares for the most precise trimming operation in the world.
We don't use saws. We use a water jet streaming at 3 times the speed of sound.
The water cuts cleanly without generating heat, preserving the strength of the composite material.
In seconds, the iconic silhouette of the enhanced combat helmet is revealed.
Now we need mounting points. The helmet is locked into a heavy-duty drilling jig.
Automated drills bore holes for the chin straps. Placement must be accurate to within a single millimeter.
Any crack or delamination here means the helmet is scrapped. Perfection is the only standard accepted.
Human hands return to smooth the raw edges. No sharp points can remain to irritate the operator.
To seal the layers, a durable rubber edge band is applied around the entire rim circumference.
Heat is used to shrink the rubber, creating a watertight seal that protects the composite core from moisture.
Before painting, the surface must be surgically cleaned. Every speck of industrial dust is washed away.
Now, we go tactical. The bright white shell is about to disappear into the background.
Even a single fingerprint could prevent the protective camouflage paint from bonding correctly.
First, a primer coat bonds to the polyethylene shell, creating a solid base for the camouflage layers. UV lights cure the primer instantly. Speed and consistency are essential in mass production.
Next, a texturizing agent is sprayed. This rough surface is vital for field operations.
With the texture set, the helmets are ready for their true colors.
It stops sunlight from glinting off the helmet, which could visually give away a position.
Robots apply the final top coat: olive drab, desert tan, or coyote brown.
The robot's path is programmed to ensure the paint thickness is identical on every curve of the shell.
Now they look like standard issue gear, but they are just empty shells. It's time to add the internal systems.
They pass through a long infrared oven. The paint is baked on, becoming scratch-resistant.
Inside, heavy-duty Velcro discs are installed. These will serve as anchors for the suspension system.
7 independent memory foam pads are inserted. They absorb the energy of kinetic impact.
The chin strap hardware is bolted through the pre-drilled holes with high torque.
On the front, the optical shroud is bolted on. This aluminum bracket holds night vision or thermal optics.
This 4-point retention system ensures the helmet stays stable, even during high mobility maneuvers.
Side rails are added. These allow operators to mount lights, cameras, and communication headsets.
It weighs less than 3 pounds, yet it offers more protection than any helmet in history.
A final touch: the label. Lot number, date of manufacture, and country of origin. But before a single crate leaves this factory, the lot must be proven in the laboratory.
Random samples are pulled from the line for destructive testing.
Welcome to the Ballistics Lab. This is where the engineering is put to the ultimate test.
The helmet is strapped to a head form filled with calibrated modeling clay designed to simulate density.
The test? A high-velocity projectile launched from a test cannon at point-blank range.
Launch. The projectile travels faster than the speed of sound towards the target. Impact. The helmet absorbs massive kinetic energy in a fraction of a millisecond.
The projectile does not penetrate. The polyethylene layers trapped it completely.
But stopping it isn't a fuff. We measure the energy transfer into the clay. If the dent is too deep, it fails.
This batch passes. The backface deformation is within survival limits.
With the test passed, the production run is certified for deployment. They are packed into crates, destined for logistics bases in Europe, Asia, and the Middle East. Thousands of units leave this loading dock every single month.
For the men and women downrange, this is more than just manufacturing. It is the difference between a bad day and the last day. This is the modern shield, built to survive.
American engineering, American labor, protecting those who serve.